Okay, this is our second problem for today. So please pause the video and read the problem, and then I will show you the solution. Okay, so basically, the problem that we have is that there is a tank that is filled with water. Okay, so there's water in this tank, and there is this paddle wheel in the water, right? And this can rotate around like this, right? And as it rotates, these paddles will have some friction to the water. So basically, the water will hinder the movements of these paddles. And basically, it is going to do some work on the water, and that work will be transformed into heat, right? So that is what's happening here in the water. And you can see that here there's a string. It goes through these pulleys, and it is connected to a body. And this body is going down, right? And the problem tells us that it's going down at a constant velocity. What does it mean? It means that basically the drag force exerted on this paddle wheel by the water equals to the force with which this body is pulling the paddle wheel, right? So basically all of the work that is done by this body on the paddle wheel is going to be transformed into heat. Okay, so what is happening? This body is going down. As it goes down, its its potential energy will be transformed and it will be transferred to this paddle wheel, and basically the friction force here in the paddle wheel will turn that energy into heat. Okay, so all of the potential energy change of this body will be transformed to heat on this side. Okay, let's say that this have some m water, this have some m body. Okay, so the problem tells us that m water is 100 grams. So let's change this over quickly to kilograms. So 100 grams is 0.1 kilograms. We also know that the mass of this body, this heavy body, is 10 kilograms. So MB is 10 kilograms. And the problem tells us that the initial temperature of the water is 280 kelvins. So T null is 280 kelvins. It tells us the specific heat capacity of water, which is 4.2 kilojoules per kilogram Kelvin. So CW is 4.2 kilojoules over kilogram Kelvin, and let's change this over to joule over kilogram Kelvin. So because that is the basic unit, so that is 4200 joule over kilogram Kelvin. And it also tells us that this body drops 10 meters. Okay, so the delta H is 10 meters. So this body goes down. So this delta H distance. So this body goes down 10 meters until it reaches the ground. Okay. So our first task is to calculate the temperature increase of the water. So basically what happens? What happens is that as this body goes down, its potential energy is transformed to heat. Okay, so I can write down that the potential energy change here is m times g times delta H, right? M times G times delta H, and that is the amount of energy that goes into the water, and that is going to be transformed into heat. And you know the formula for the heat transfer is C times m times delta V, delta T. So that is C water times m water times the temperature change. So that is always the final temperature minus the initial temperature. So T equilibrium, T, so let's call this T1. Okay, let's make this T1. So T1 minus T0. Okay, and yeah, I missed a B here because this is the mass of the body. Okay, all right. And you can see that in this equation I only have one unknown, this T1. Okay, so I bring all components, all terms that contains T1 to one side, everything else to the other side, and then I divide everything by this constant multiplier of T1, and from that I will get the value of T1. Okay, so from this T1 equals, so I had this MB times G times delta H on the other side, and I also have to bring this CW times MW times T0 to the other side. You can see that here it was a minus sign. When I bring this over to the other side, it will have a plus sign. So CW MW T0, and I have to divide everything by the constant multiplier of T1. This is the CWMW. Okay, and that's going to be the final temperature. So once again, you can see that I know the value of every parameter here in this formula. Well, the problem didn't tell me the value of G, but we know that that is roughly 10 meters per second squared. So all that is left is to type this into my calculator. So the mass of the body is 10 kilograms times G, that is also 10, times delta H, that is also 10. So that was simple, that was 1000. Okay, so this is 1000 plus, I also need this CW times MW times T0. So that is CW, that is 4200, times MW, that is the mass of the water, that is 0.1 kilograms, times the initial temperature of the water, that is 280 kelvins. So 117600, 117600, 117,600, and divided by CW times MW. So that is, well, that is easy because this is 4200 divided by multiplied by 0.1. That is just 420. Okay, 420. So this is what I have to calculate, and from this T1 equals, well, if I add 1000 to that, that is 118600 divided by 420. So that the equilibrium temperature is 282.4 kelvins. 282.4. 282.4 kelvins. So you can see that this body that is 100 times heavier than the water, right? This body is 100, because this is 10 kilograms, the water is just 0.1 kilograms. So this body is 100 times heavier than the water, and it drops 10 meters, right? So it does a lot of work, but all of that work is only enough to raise the temperature of the water by about 2.5 or 2.4 kelvins. Okay, so you can see that to raise the temperature of something, you actually need a lot of heat, right? So the second part of the problem is that it asks us to calculate the entropy change of the water, and and this is where you should remember that big logarithmic formula for the entropy change, or if you don't remember it, deduce it. Remember in the previous problem I showed you how to deduce that formula, and also in the lectures I showed you how to deduce that formula, but I think it's easier just to remember it. This is C times M times ln the final temperature divided by the initial temperature, so this T1 over T0. And of course, because we have to calculate the entropy change of the water, then we need the specific capacity of the water and the mass of the water, right? And you can see I know everything in this formula, so all what is left is just to type this into my calculator. So here, CW is 4200 multiplied by MW, that is 0.1, multiplied by the natural base logarithm of 282.4 divided by 280, close the parenthesis, hit enter, and that is 3.585. 3585, 3.585, and this is in joules over Kelvin, because remember here in the beginning I changed everything into basic SI units, so this is also in basic SI units, so that's the final answer. Okay, so this was problem number 2. Basically, the only difference between this and the other problem is that here the heat was not coming from a hot object, it was coming from mechanical work. Okay, so please note that you can have problems where mechanical work is transformed into heat. Okay, all right. So this was problem number 2. See you soon with problem number 4. Sorry, problem number 3.